Hello everyone. In a previous video, I actually used Maxwell's equations, the four equations, the divergence and curl of the electric field and the magnetic field, to derive a set of vacuum equations, equations in which there's no sources for the electric magnetic field, i.e. there's no J and there's no rho, and use that to compute actual wave equation for both the electric field and the magnetic field. I got two separate wave equations, and later I'm going to show you that a plane wave is a solution, and I'm going to find out some very specific properties of how the electric field, magnetic field, and the velocity of the wave are related. But right now I wanted to show you from the wave equation that the MuZero times EpsilonZero that was sorted in the slot of 1 over the velocity squared does indeed have the proper units. So let us get started by me showing you my document cam, and I'll refresh what we've found. So what we found when we were doing that derivation is we found that the second derivative of the electric field with respect to x squared plus the second derivative of the electric field with respect to y squared plus the second derivative with the electric field with respect to z squared was actually equal to MuZero, the permeability of free space, EpsilonZero, the permittivity of free space, times the second derivative of the electric field with respect to time. And in fact, this was a vector equation, so I could actually put that up there. There's a shorter way of writing this using vector notation, and that is basically that this is the del squared operation. So it could be written del squared E equals MuZero EpsilonZero second partial E with respect to t squared. And then, of course, we found the exact same equation for the magnetic field. Del squared B is equal to MuZero EpsilonZero second partial B with respect to t squared. Again, this is in the SI units. We could do this with the Gaussian units and that sort of thing. But in these units, of course, the electric field has units of volts per meter or newtons per coulomb. The magnetic field has units of Tesla. And what I'm going to show you is that the general form of a wave equation, namely del squared phi, say, is equal to 1 over v squared second partial phi with respect to t squared. I'm going to show you that this actually has the units of velocity when I put it in the proper form. And that proper form, of course, would be something along these lines. Del squared E is equal to 1 over the square root MuZero EpsilonZero squared. Notice that when you square this, it becomes 1 over MuZero EpsilonZero. And since it's in the denominator, it'll become MuZero EpsilonZero up at top, which is just what we had. But the equation requires the velocity to be in the denominator. So that is really what we're showing, is that this 1 over the square root of MuZero EpsilonZero has the units of meters per second, and I'll actually then calculate MuZero EpsilonZero with our best values and take the square root, flip it over, and you'll see that it does in fact give us the velocity of the speed of light, or the velocity of light. So let us begin by saying I want to know the dimensions of 1 over the square root MuZero EpsilonZero, which I can also write as MuZero EpsilonZero units, which I might even break up into two separate boxes like this, raised to the negative 1/2 power. Or I can similarly write basically MuZero times EpsilonZero unit wise, that's what the brackets mean, remember, to the negative 1/2 power. So in order to do that, I got to figure out what these units are for MuZero and EpsilonZero. And the equations I'm going to use for that are basically one of the results we get for Ampere's law, from Ampere's law, or we can get it from the law of Biot-Savart, namely that the magnetic field B around a current carrying wire is MuZero I over 2 pi times R. So from that, I can see that the units of MuZero should be equal to the units of the magnetic field, which is the Tesla, times the unit of the distance, which is the meter, divided by the unit of the current, which is the amp. So that's one of the things. I can also use Coulomb's law. F is equal to Q1 Q2 over 4 pi epsilon 0 r squared to find out what the units of epsilon 0 are. And the units of epsilon 0, you can see, is Coulomb squared per, this will come down here, that becomes a Newton, and then that's a meter squared. So we got that. Now you can see there's a little bit of a problem in that I still have that Tesla that isn't going to go anywhere. So if I also use the equation F is equal to Bill sine theta, which you might recall, then I can also reach the conclusion that the unit of the magnetic field, specifically in this case the Tesla, is equal to the Tesla, but that turns out to in fact be equal to not just the Tesla, but the Newton, because we're solving for this, that'd be the Newton per amp meter. So Newton per amp times meter. Those are the things we need. So now I'll go on from there and compute what this quantity here is. So again, I'm going to write my curly bracket, raising to the negative 1/2 power. I'm going to replace MuZero with Tesla meters per amp. And then I'm going to replace epsilon 0 with Coulomb squared per Newton meter squared. And all of this, of course, would be to the negative 1/2 power. I can actually make some cancellations there. I can see that, for instance, this meter down here is going to cancel out with that meter up there. Now I can also get rid of the Tesla by using this relationship right here. So I'm going to take that Tesla and I'm going to replace it with, in this case, newtons per amp meter. So Newton per amp meter is the Tesla. And that, of course, will be divided by the amp. I already counted out that meter. And then that's multiplied by the Coulomb squared per Newton meter. Remember, we already counted out that one. And of course, this is still to the negative 1/2 power. So when I do that, I can now see that the Newton is going to cancel out with the Newton there. And I will get, in this case, a Coulomb squared over, now I have, this is going to come down to the bottom, so this will be an amp squared, and then a meter times a meter would be a meter squared, and I think that just about does it. There's a Coulomb squared, there's the amp times the amp, that's the amp squared, the meter times the meter, that's the meter squared. So this is really all there is. Now we just recall that, in fact, the amp is a Coulomb per second. So I can now say Coulomb squared per Coulomb per second squared. And that's just from amp, which is current, is dq dt. So that would be Q, the unit of charge is a Coulomb, and T is the unit of time, which is seconds. And that'll be Coulombs per second quantity squared times meters squared. And that's to the negative 1/2 power. If I continue on this way, you can see now that the second squared is going to become on to the top and the Coulomb squared will be in the bottom. So I'll have second squared per meter squared times Coulomb squared per Coulomb squared. And in this case, the coulombs are canceling each other out. Notice how I use different symbols to cross things out for each part. That way I can trace back and see exactly what I'm calculating things, canceling things out with. That's raised to the negative 1/2 power. That, of course, is seconds squared per meter squared to the negative 1/2 power. So basically, I'm going to flip it over to get rid of the 1/2. That gives me meters squared per second squared, excuse me, to get rid of the negative, meters squared per second squared to the 1/2 power, which once you take the square root, you get meters per second. And of course, we've now shown that the velocity, or the epsilon 0 times MuZero, does in fact have the units of velocity, namely meters per second. So we have shown that part. Now, in principle, that means the actual velocity should be the speed of light, because that was one of the big things when this came out. Then all of a sudden you instantaneously know what the speed of light is. And in fact, if you take 1 over the square root of MuZero epsilon 0, it turns out that that is 4 pi times 10 to the negative 7th. And remember, that was Tesla meters per amp. So I can write it this way. And then I have that times, and I looked up a particularly precise unit of, or excuse me, rendition of epsilon 0. That's 8.854187817, and that of course is Coulomb squared, times 10 to the negative 12th Coulomb squared per Newton meters squared. We've already worked out the units, so I'm going to drop these in a second. But basically what we're going to do is compute all this and raise it to the negative 1/2 power. When I multiply, in fact, 4 pi, so I'll do 4 times pi times 10 to the negative 7th, and then I multiply that by 8.854187817 e to the negative 12. I get 11.1265. And that's all my calculator is showing right now, but my calculator keeps quite a bit more digits than that, and it's 10 to the negative 18th. That's just the product of what's inside of here. We know the product of what's inside of here is going to give us units of seconds squared per meter squared, because we're then going to take this and flip it over and take the square root. So when I actually do this times this, I get that number, 11.1265. Again, my calculator gives more digits than that, but this will be raised to the negative 1/2 power. So I'm going to say raised to the negative 0.5 power. And lo and behold, I get 2999792. And in fact, it should be 458, and in fact it is. So I looked at my calculator, it says 458.01051 meters per second. And that is the speed of light, 299,792, or excuse me, 299,792,458 meters per second is the speed of light. So we've now seen that Maxwell's equations can in fact produce wave equations. And what it does is it produces a wave equation for the electric field, produces another wave equation for the magnetic field, both of which have a velocity MuZero epsilon 0 to the negative 1/2 power, and which happens to be the speed of light. I will show in a later video that if you assume that the solution is a plane wave, you can actually see that the electric field and the magnetic field are mutually perpendicular to each other, and that they're in fact mutually perpendicular to the velocity, such that if you put the electric field on your index finger and you put the magnetic field on your middle finger, then your thumb points in the direction of the velocity. So E cross B is equal to basically the K vector, which is a vector that points in the direction of velocity propagation, but it's 2 pi over lambda. So I think that's a good intro to showing you that the wave equation does in fact give us a wave equation, and that it does in fact turn out to be a velocity having the speed of light. So I think that's a good point to end this video. Have a good day.